Okay, so in this video we're going to start our discussion on vectors. Okay, and this video will focus mainly on the basics. Okay, so we'll talk about what vectors are, and then we'll also talk about how to use vectors and perform certain operations on vectors, mainly addition and subtraction. All right, so there are many real-world problems where we have to use certain there are many real-world problems when we have to use both a number value and a direction, okay, particularly in physics. Okay, an example would be when I need to know the direction of a car, and I also need to know the speed of that car. Okay, so normally I'd have a car, and if you ever watch your dad driving, in your car you have something called a speedometer, right? And this measures your speed. But this doesn't tell me the direction that I'm going in, okay? And so there are certain quantities that we use called vectors where we assign it both a number value, a speed, and a direction, okay? So we would actually call that velocity, okay? Velocity has a very specific meaning in physics because it indicates direction as well as how fast an object is moving. Okay, so let's back up a little bit and generalize this. Quantities that have only magnitudes, okay, where we only have a length or a size or some numerical value, those quantities are called scalars. Okay, and if we have if it's a quantity that has both a magnitude and a direction, we then call that a vector. Okay, so a vector is a quantity that has both magnitude and a direction. Here are some real-world physics examples for those of you who like physics or have studied physics. Scalars, an example of a scalar would be distance. Okay, the length from here to Busan, right? That would be the distance. That would just be a scalar quantity. Speed, if I was to take a watch and measure how fast you were moving, that would tell me your speed. Okay, I could calculate your speed. Time is measured as a scalar. Okay, but there are certain things where there are certain instances when we're interested in the direction as well, and so displacement would be a vector quantity. If this is defined as, okay, so displacement is defined as a distance plus a direction. Okay, so I could say if I am for instance, if I was here, okay, and then I moved over to here, okay, then I would say, well, I have been displaced this length, okay, in this direction, with this angle. So I've indicated a direction, and I've indicated how far I am from this original point. Okay, so that would be an example of a displacement. This arrow here would be called the displacement vector. Okay, so it's a quantity. The displacement is this vector. It's a line it's an arrow really with a direction. It's a certain length and a direction. Okay, velocity is another example. I could say I'm moving at a certain speed and in a certain direction. Okay, I could be moving this way, I could be moving this way, I could have a car going in all of these different directions. Okay, so all of those would be vectors. Okay, whereas if I was just talking about speed, they could have the same speed, but I wouldn't know the directions. Okay, acceleration, force, momentum, all of these are topics and concepts that you'll learn about when you go to physics, but they are all vector quantities. Okay, whoops. Alright, so if I want to draw a vector, basically I'm going to use an arrow and an angle, okay? But the direction, okay, the angle would be used to show the direction, and the length of the arrow would be used to show how long it is, okay? How strong that vector is, or how far away that vector is, okay? So this would be the magnitude part. The length of the arrow would be the magnitude, and the the direction would be indicated by the angle. Okay, so here would be an example. If I said draw a vector that has a magnitude of 2 centimeters and a direction of 45 degrees in the southeast direction, and I say draw it to scale, okay, most of the time we're not going to be drawing it to scale, but if I did say draw it to scale, then you would have to draw a length. Okay, so let's say 1 centimeter. Sorry, this should be kilometers per hour. If I said draw this vector 2 kilometers, a vector that represents going 2 kilometers per hour in the 45 degrees southeast direction, okay, then I would draw an arrow that is 2 centimeters in length. Okay, so this would have to be 2 centimeters, and the direction would be indicated by this this angle. Okay, 45 degrees in the southeast direction. Okay, but most of the time we will not be looking at vectors that are drawn to scale. Okay, we will just be using simple diagrams to draw vectors. Okay, but this is just an example to give you an idea of what vectors might look like. Alright, so let's talk about notation here. A vector, usually we represent that arrow. We have to quantify this basically, right? We have to somehow, we can't just be drawing random arrows, so we have to show from where to where the arrow is going. Okay, and so we say that we draw usually the starting point and the end point, and the vector then, if I'm going from O to A in this case, and it's going between these 2 points, then I say this vector is called OA. This is the vector OA. And notice here that I have 2 different types of notation here. I have a half arrow on top, and I have a full arrow. Okay, I can choose either one. These are both okay. All right, but I prefer to use the half arrow just because it's a little bit faster. Okay, and when you write these vectors, the order of the letters matters. Okay, we always start from the tail end of the vector always represents the starting point, and the tip end, or the head of the arrow, represents the arrow that the direction that it's going towards. Okay, and we say OA is a position vector. Okay, it's a position vector of A relative to O. What this means is it's saying A is at a position away from O that's represented using this arrow. Okay, it tells me the position of A relative to O. That's what this vector is telling me. So if I see OA vector, vector OA like this, we say this is the position vector of A relative to O. Okay. You can also label vectors. So we labeled a vector using this method with points, but you can also label a vector just by using a simple variable. Okay, so I could say A and use a half arrow on top of it. Okay, a half arrow or a full arrow, it doesn't really matter, but those both represent vectors. So this would be the vector A. Okay, I could call this the vector X, and that would also be the same vector as the vector OA. Okay. Now, something to note here: when you read your textbook will use a bold-faced letter for vectors. Okay, you are not allowed to use bold-faced letters when you are writing vectors out on paper. So if you say, this is vector A on your paper, okay, I will not accept that because it's too confusing to write it as bold-faced letters all the time. So when we do it in writing, we always use the arrow notation. Okay, so keep that in mind, please. Always use arrows when you're writing on paper. Okay, it can be very confusing because later on, if you don't write the arrow, it becomes just a variable, and your answer would be incorrect. So please don't do that. Magnitudes. Magnitudes, we said, was the length, right? We said it's the length of the arrow. and we represent the magnitude of an arrow or a vector. If I've written it in this form, we say the magnitude or the length of this vector is just the distance OA, right? And that makes sense. That's just the distance from O to A. So that tells me the length of that arrow. Or we write these bars, okay? It's basically an absolute value sign on either side of that vector. So I'm going to leave the arrow inside, I'm going to leave it in the vector form, and then I'm just going to add 2 bars, or I'm just going to take everything away and write it as a distance. This is a geometric notation, isn't it? And then I can also write it, if I have a vector A in this form, and where I don't have points anymore, but just a letter, okay, then I would have to write it in absolute value form. This is not an absolute value. This means, okay, this means magnitude, not absolute value. It's the same symbol, but it means something different, okay? So if you see this little arrow inside the absolute value sign, that's a magnitude, not a absolute value. Some books will teach you the magnitude to be written with 2 double lines like this instead of single lines. You can choose either one you want, but for this course and for the DP, we will be using this notation. All right, and here are some properties of vectors that I do want you to know. Okay, I can freely move if I have a vector, okay, like this. I can freely move this vector anywhere I want to, and it does not change the vector. Okay, so if I have a vector A, I could move it to over here, and I could move it to over here. Whoops, that doesn't look like a vector. I could move it to over here, and it would remain the same vector. Okay, all of these vectors are the same. Okay, but there is a condition for doing this. I can move them around only if I don't change the length or the direction. So I can't change the length or the direction. As soon as I tilt it like this, that's a totally different vector. These are not the same vectors anymore. Okay, if I change the length, that's not the same vector anymore. Okay, but if I keep it the same vector, if I keep the length the same and the direction the same, these are all equal vectors. Okay, so basically shifts are allowed, but not rotations or stretches. Okay, and that's what this next section's on. Vectors are equal if they have the same magnitudes and the directions, which means I can move them around anywhere I want. I can translate them anywhere on the plane. Okay, as long as I don't change the direction or the magnitude. 2 vectors are parallel then, okay, if they go in the same or opposite direction. And that makes sense. If I have a vector here and a vector here, okay, they are not the same anymore, but they are in the same direction, so they are parallel vectors. Okay, and I could also have this vector over here, and these would be parallel, and these would be parallel, because they're going in opposite directions. Okay? Negative vectors have the same lengths, but opposite directions. So, for instance, I have vector A, and this vector then would be minus vector A. Okay? They have the same lengths, but one is going in the opposite direction, so we say it's negative A. Right? Here's some additional examples. If I have A and B in this case, we would just conclude that the relationship between these 2 vectors are that they're parallel. If I have 2 vectors like this, A and B are parallel and the lengths are the same. But they're going in opposite directions, so we would say that A could be rewritten as negative B, the negative B vector. And vice versa. I could say that B is equal to the negative of vector A. Okay? So these are some conclusions that I can make about this. From this picture, I would say that vector A and vector B are the same vector, or they're equal vectors. Okay? Since they are going in the same direction, they are both parallel, and they have equal magnitudes. Alright, let's look at one more example here on the basics of vectors, and then we'll move into addition and subtraction. Vectors, find the vector expressions for the following in terms of the vectors a and b. Okay, so what is BA? What is the vector BA? That means starting from B going to A, BA, if we need to write our vector in terms of A or B. Okay, and we're going to assume this is a parallelogram. I didn't write that in here, but this is a parallelogram, okay? Okay, so it's a parallelogram, which means that this is parallel, these are parallel, okay? And they're all the same lengths as well. Sorry, these two are, the opposite sides are of the same length, okay? So that's a parallelogram. Okay, now let's see, what's BA going to be in terms of A and B? All right, well, what other vector is BA equal to? BA is equal to the vector AB, except it's backwards, right? It's going in the opposite direction. So we could say BA is really just the A vector, because the length is the same, but it's going in the opposite direction. So we would say it's minus the vector, the negative of vector A. So what would C be then? If I'm going from C to B, that would be minus the vector B, right? Going from A to D, remember we said we can move vectors around, so I could take this vector and move it over here, since I know that the lengths of this are, these are going to be the same and the directions are going to be the same, right? Because we have a parallelogram, they're parallelograms. This is a parallelogram, sorry. So AD would be the same vector as BC, so this would actually be vector B. I could say it's equivalent. CD would be the same as BA, and we already found BA, so that would be negative vector A. Okay? All right.